environment. And we have a label that also is helping us with this. So I think it's already started. Gabriel, are you ready? So,
thank you. Thanks a lot for inviting me. I'm really happy to be here. Yeah, my name is Kuba, and I'll be staying with you for this week and teaching in the camp for the next 5 days. So the plan for today is we'll start with some warm-up. We'll start with some exercises. I don't want to start with a lengthy lecture. Out of the exercises, we'll switch to, I guess, some short lecture, and then we'll have a lunch break. After lunch break, we're going to have a 5-hour contest. Okay, but before we start, I'd like to first thank you for filling in the survey. I got lots of answers, and I read all your comments, and I should say that from the comments, I could see that you're really motivated, which is really great. Lots of comments were like, don't be afraid of giving us some very hard tasks, and we'd really like to get something super hard from you. And I think my favorite one was simply, please don't have pity. So yeah, actually I should explain that it's not that I wanted to make things very easy. This wasn't the goal of the survey. The main reason was that I didn't really want to give you some tasks which, for example, requires some theorem that nobody knows about, because this makes no sense, right? I mean, after the contest, you know, oh, that. So this is what I should have done to solve this. So don't be afraid. You're really going to get some very hard problems this week. Second thing, I'd like to ask you about our questions. So please ask me lots of questions. Interrupt me at any moment. Actually, if I don't get too much questions, I get quite confused, because it means what I'm saying is either too easy or too hard. So it's really much easier to work if I'm getting questions. And the third thing for the beginning is some advice for you. So my advice for you is to think of the goals you'd like to achieve during this camp. So think of maybe the areas you'd like to improve on, or the algorithms you'd like to learn, or the results you'd like to achieve, and try to work in a way so that you're going towards it, so that you pop up. And not only for the entire camp, but also every single day after every contest. See which task you have solved, see which you couldn't solve, and find maybe 2 or 3 tasks that you'd really like to understand and study them, maybe code them again, and then try to and not only try to solve them, but also try to think like, well, okay, I didn't manage to solve this one, but what should I have done to actually get to the solution? Because, you know, it's not that you know the solution. If you know the solution, okay, then the task is easy. But what you should learn is that, okay, what is the way to get here? What was the way to get to that solution? What was the required way of thinking? And I think that's very valuable and worth trying for you. Okay, so what I'm gonna concentrate on during this week is, I think, algorithmic thinking. So I'll try to maybe not give you some well-known textbook algorithms, but rather try to talk about stuff that shows you various algorithmic techniques and the way of reasoning that you might use to solve some problems. I think I wouldn't really focus too much on coding. I believe that if you want to learn to code better, you have to just practice a lot. Maybe the one piece of advice I could give to you is that if you really like to improve your coding, you should solve lots of tasks, but do not stop after solving one. I mean, if you solve the task, then okay, you get some problem accepted, but then it's very important to analyze the code you've written. So it's great if you can find some solutions of some other people. So Top Coder is a great resource here, because you can solve a task and then see how the others did it, and then you may find lots of useful tricks and methods for writing the code in a clear and easy way. So yeah, I believe that the coding is kind of in a big part individual work, but also don't forget about analyzing what you're doing. Right. So during this week, we're going to focus on algorithms, and today, as a warm-up, we're going to start with planar graphs. Planar graphs. I chose this topic, well, for two reasons. One reason is that I believe, although they are very specific in classical graph, really solving problems with planar graphs requires lots of different algorithmic techniques, and it demonstrates various ways of algorithmic thinking. And well, the second reason is that I've been also doing some research with that, so it's a topic I really like to share it with you. Okay, so let's get started. Planar graph. What is a planar graph? Planar graph, well, I guess you all know that, but let me draw one. So it's a graph which you can draw on a plane in such a way that the edges do not intersect. So this is a planar graph, and an example of a small non-planar graph is something like this. Here on the left, here on the right, everything connected to each other, or like this. 5 vertices, everything connected with each other. And actually, these are the two canonical examples, meaning that, well, if this guy or this guy is in some sense inside the graph we have, our graph is not planar, and if those guys do not appear inside, then we're sure the graph is planar. I mean, they are inside in the sense that, you know, if we insert a vertex here, the graph still isn't planar. I mean, this isn't any easier to be drawn in a plane. But let me not go into details here. This is quite theoretical, and I'm not sure it's really useful for us. So the planar graph has, well, as every normal graph has vertices. It has edges connecting them. But also, once we draw a planar graph in the plane, it has faces. Face is a region enclosed by the edges. So this is one face. This is another one. There are 4 faces, and there is one infinite face around all this thing. So as I said, planar graphs are very interesting, and the reason for that is that lots of algorithmic problems become much easier if we're working with planar graphs instead of general graphs. So a great example is max flow. Max flow, you can, I think in a general graph, if you want to compute max flow, you'll need time with, okay, there are many options, but one of them is something like n cubed, number of vertices cubed. That's time needed to compute max flow in a general graph. In a planar graph, what would be your guess? What's the running time? Linear. Oh. I know where you're saying that. No, it's actually not linear. It's almost that. It's n log n, so it's slightly less than linear. Yeah, I'm glad you said that. I should confess that in the survey there was one very nasty question, the one that asked about linear time algorithm for max flow in a planar graph. I'm afraid such an algorithm does not exist. But still, I think there were 2 responses that, like, I kind of know how to do that. But yeah, I think this was just a nasty question. So in planar graphs, max flow gets very, very very fast. And the same is for many other problems, like for shortest paths. If you want to compute shortest paths in a planar graph, you just need linear time. The algorithm is super complicated. I mean, I tried reading it, but I just couldn't understand it, and that's the case for most people I know. But, well, okay, in theory, you can do that. And today, I'd like to show you some examples of how things get easier when we're working with a planar graph. And in order to do that, we're going to discuss 4 techniques that can be used to achieve. We'll start with the easy ones and then get to the more advanced ones. So I think many of you would know the easy ones, but still, let me start and with those and review them. Okay, so the first thing that comes in handy is Euler's formula. Okay, who of you have seen this? Half of you. Okay, so what does it say? Well, if we denote by V the number of vertices, with E the number of edges, with F the number of faces, and with C the number of connected components. Then, let's see. Then what we get is V minus E plus F equals C plus 1. This thing holds. Why does it hold? Well, this formula can be proved inductively, so this is a side note. So if we have a tree, is a perfectly fine planar graph. We can draw it in a plane so that edges do not intersect. And in a tree, we've got V equals sum. Okay, we've got let's assume for now that we have just one connected component, C equals 1. So the simple case of a graph with planar graph with one connected component is a tree. And in a tree we have the number of edges is equal to the number of vertices minus 1. And the number of faces here is 1. And if we plug in those, there we get equality. Great. Now, of course, not every planar graph is a tree. There are also some others. But we can see that if we start adding more edges here, then basically adding every single edge will increase the number of edges and increase the number of faces. We're cutting one face in half. So this thing increases by 1, and so does this thing. So they both increase by 1, so this cancels out and it still false. This shows that this formula is true for every connected planar graph, and also from there it's easy to go to disconnected ones. Okay, so why is this thing useful? Well, for 2 reasons. One reason is that sometimes we really need to count some things. So there are many problems in which you'd like to count the number of faces, edges, or vertices, or whatever in a planar graph. And it's often the case that, for example, counting vertices and faces is easy, and if you can count those, you can get the count of edges, or any other combination. We can count it suffices to count the number of vertices and edges, and we get the face count. All possible options are given here. But the second and probably even more important consequence is that from this formula we can prove that planar graphs do not have many edges. Why is that? So what is the maximum number of edges in a planar graph? So say we have a graph which looks like this. So first, because we like to bound the number of edges, let us add here as much edges as we can, preserving planarity. So we can add this edge, an edge like this, and then another one like this, and am I done or not? Can I add anything more? I think I got it. So if I take a planar graph and add as many edges as possible, what I get in the end is that every face has exactly 3 sides. So because otherwise, if I have a face with 4 or more sides, I can add one more edge. So if I keep adding edges as long as possible, in the end, I have that the number of each face has exactly 3 sides. Now, if this is the case, then I can say something about relation between those numbers. So if every face is a triangle, then for every face it has exactly 3 edges around it, and for every edge there are exactly 2 faces on both sides. So in some sense, each face can be assigned half of the edges around, right? This edge is kind of split between those faces. So I can say that maybe I should put it this way. If I put a number 3 on every face and then transfer 1 unit to every edge, then I put a load of 2 on every edge, right? Each edge gets a load of 1 for both sides. So I put a load of 3 times the number of faces first, and in the end, I get a load of 2 on every edge. Make sense? Yes? No? Okay. So I have this identity, and if I plug it in, I got that. Okay, now. Which one?
2, 3F.
This thing, right? Okay, so what I have is a planar graph in which every face is a triangle, right? So I'd like to get a relation between the number of faces and the number of edges. So I do the following. I take each face and I put 3 tokens on every face, right? So I put 3F tokens in total, right? So 3 tokens on every face. Now I do the following. For every face, I take those 3 tokens and distribute them 1 token to each edge. There are 3, so I can put 1 token on each of them. If I do this, then every edge will receive 1 token from its one side and another token from its other side. So now I have 2 tokens on every edge, right? So since the number of tokens before and after is the same, I get equality. Make sense? Okay, so I have this. I wanna plug it in here, and I get calculations.
Uber.
Yep.
And the other face, the effect face, will distribute more than 3 tokens in the example.
Well, I assume that every face here is a triangle.
But the other face, the
other face here is also a triangle, right? 1, 2, 3. So actually, yeah, the outer face seems to be like a different from the other faces, but actually it's not. So you can you can imagine that the graph is drawn on a sphere, right? And if you do that, then every face is the same, right? There is no outer part. Or the other way to put it is that if you have a planar graph, it has some outer face, but you can kind of take any face you want, like this one, and switch it. So you kind of turn it around so that this thing becomes the outer face and it all goes inside, right? So there are basically for every planar graph you can swap the drawing so that any face becomes the outer one. And although it's on a plane it's different, it's actually not much different from every other face. Right, so let's get back here. So we plug this thing here, and we get an F is that E is equal to 3 over 2F, and we've got V minus, which way do I want to go? No, it's the other way. I want to say that F is equal to 2 over 3E. And then I plug this in and get V minus E plus 2 over 3F is equals C plus 1. Okay, let's assume that there's just one connected component. So this equals 2, and this is E, right? This is E, so I got V minus 1 over 3E equals 2, so V is equal to, sorry, I'm bad at calculations. E, and the way I want to actually have it is that E is equal to 3V minus 6. Okay, this is the way I wanted it to happen. So what we got here is that if we take a planar graph and as many edges as possible, we get this equality. So in general, if we didn't add as much edges as we could, so the number of edges, so this is the upper bound on the number of edges. In general, we have that the number of edges is at most 3b minus 6. So the great conclusion here is that planar graph cannot have many edges, just at most this thing, so this is basically linear in the number of vertices. And this is a very useful property. And maybe even more useful is another consequence of this formula. So if we have that E is at most 3b minus 6, then what we might infer is that there always exists a vertex of degree at most 5. Well, why is that? So if every vertex had more than 6 edges, then basically this wouldn't hold. We'll have too many edges for this to hold. So whichever planar, if we draw any planar graph, there would always exist a vertex with at most 5 incident edges. And I would say that out of the things, out of the consequences of Euler's formula, this is probably the most useful one for building algorithms. Okay, so that was some introduction, and now let us use this stuff. So the way I'd like to do it is I'll give you some tasks to think about, like 4 exercises and 5 to 10 minutes, and I'd like you to try to solve as many as you can. You can work in groups, you can work alone, and after 5, 10, 15 minutes, we're gonna discuss them. Let's see, what do I need to do? Yeah, erase this. So I guess some of you might know some of the exercises, but I hope nobody knows all of them. So the tasks are, and the exercises are as follows. Yeah, I should put it here. Right up here. Okay, so the first one is everyone will start with you're given a planar graph G, and so I'm not going to write this many times. So the first one is if we have a graph and would like to ask questions like, are those two vertices connected with an edge? Then, depending on our representation of this graph, we can answer these questions in different ways, right? If we have a matrix which for every pair of vertices says if there is an edge or not, then we can do it in constant time, but we use lots of memory. If we have adjacency lists for every vertex, then we can go through the adjacency list of every vertex and find the edge. But in theory, that would be slow. So it turns out that for planar graphs, this problem can be solved efficiently. So the task here is build a data structure that allows to answer queries like are vertices U and V connected with an edge? It's not are they in the same connected component, but is there an edge connecting them? And this has to be done fast. Like we have like and time for preprocessing, and answers should be given in constant time. Second one is color the graph with 6 colors. What does that mean? Well, I want you to find an algorithm that assigns 6 colors to vertices of the graph in such a way that 2 vertices connected with an edge get different colors. And we'd like to use 6 colors for that. Third one is okay. This is about the third one is about social networks. So for every vertex, find the number of friends of his friends. So if we have a vertex, then so the graph now here is like a social network. 2 vertices here are friends if they're connected with an edge, and for every guy we'd like to okay, count. Maybe that's fine. We'd like to count what is the number of friends of all his friends, which are not his friends, right? So this is what you get in a social network, like friend suggestions. Hey, you probably know this guy, so he's a friend of your friend, but it's not yet your friend. And the fourth one, the last one, is compute minimum spanning tree in linear time. So here the edges of the graph have some non-negative weights, and we'd like to compute the minimum spanning tree of the graph in linear time. Normally you'll do it in logarithm, but here we can do this faster. Any questions regarding those? Clear? Okay, so then, okay, I think you have like 5-10 minutes, we'll see how it goes, and then we'll discuss.
The first question is like, are they the same connected component?
No, it's there's an edge connecting them. So is there an edge that connects these two vertices? And yeah, the problem here is that normally if you have a graph, so maybe I should say what is not allowed here. So it's not allowed to build a matrix of size n by n and just have ones for edges, because this matrix is just big, it's n squared. I'd like to have a data structure which is small. And also, you might, I don't know, use some set and just insert all the edges there, which would give you a small data structure, but the query would be logarithmic. Right? So what I want you to find is something which is in some sense optimal. There is just linear processing time and constant time. Okay, as I said, you can work low, you can work in groups, however you wanted to. And feel free to ask me questions at any time.
In the third question, what complexity do you expect?
Again? It will be easier to do this slowly. So I think what you get is something like that. Okay, a quick check of how things are going. Anyone managed to solve at least two? Maybe? Two, yeah? Okay, so let's then have like another 10 minutes. Take your time. Okay, let's see how things are going. So, anyone has an idea for the first one? Raise your hand. Okay, second one. All right, third one. Okay, and the last one. Okay. You want to have more time or discuss? Okay, let's discuss. First one, someone raised his hand. Can you come and show how to do it? Can you come here? Raise something. Maybe I'll raise this. I think you have to be like it's tricky, but it was like it's a life not too high, but here.
So the main idea is to use this property here. If you have, if you remove the vertex with degree at -5, you will still have a planar graph. And you have another vertex with this property. So you can keep for each vertex, you can build a list of its neighbors, but you get the vertex with this property, and when you put his neighbors in his list.
So the first step is that you find a vertex of the gate host 5,
Yes.
and then it has 5 edges, and we take these edges and assign these edges to this vertex.
Yes, that's it. And you remove these vertices with these edges, and you keep doing this. And you get a query.
So yeah, so in the end we have like every time, so at every step we remove a vertex and it goes 5 edges together with it, right?
Yeah.
And we keep repeating this, and then we delete everything, right? Because by doing so, because every time we have a vertex of this property, we remove the vertex and like together with the edges, so that now we have a list of vertex and some few edges, right? This is what we get.
Yes. And so every time you get a query, to answer this query, you have just to search the edge in the list of the two vertices. So we have at most 10, and it's so common like students.
So thanks a lot. So again, another way to look at this thing is that if we have, okay, I think other colors. Another way to look at this thing is that if we have a planar graph, this one is particularly easy because here the degrees are low, but think of this as being a part of a very big planar graph. So we can find a vertex of degree at most 5. It always exists in every single planar graph. And you take this vertex and direct all the edges incident to it to this vertex. And once we do that, we delete. We get a small planar graph and we keep iterating this idea. In the end, we direct all the edges in such a way that for every vertex there are at most 5 edges going inside it. And if so, we can, for every vertex, we can maintain all of them in a list. It's just a list of 5 elements. And then, if we have a query, this query will ask about some edge, which is directed in some way, it's either this way or the other. And for example, so we check the list of those 2 vertices, and in this case, this edge is on the list of the 5 incoming edges of this vertex. And we can answer the query. Does it make sense?
Cool. What's the time of pre-processing?
The time of pre-processing, that's a good question. So, the difficult part, I guess, is the step find the vertex of degree at most 5, right? Because, like, once we have it, we just have to delete some vertex and some few edges, which we can do. So the hard part is how to find it. And in order to do that, we maintain data structure, which for every possible degree of a vertex, so every possible number of edges, we have a list of here we have a list of vertices of degree 2. Yes, this is vertices of degree 2, and so on for every other degree. Now, we can build this thing for the initial graph easily, right? We just go through all the graph, and for every vertex, we compute it 3 and add it to the right list. That's easy. And then, what we obviously need to do is we have to maintain this thing as we are deleting stuff. So, if we get a vertex and we delete its adjacent edges, for every vertex here, we need to decrease its degree by 1. So we take this vertex and we can have a pointer from a vertex to where it is on the list. So for example, we take this vertex, this guy is here, so then we delete it from this list. It lost 1 edge, so we now add it to this list. Right? So for every edge that we delete, we can in constant time move the vertex from one list to the other. Now, if we have this data structure, then at every step we can just search, we can just check those 5 entries and find any vertex on any of those lists. This will be a vertex of degree at most 5. That's something? So in general, this can be implemented in linear time, because finding the vertex requires just searching through 5 elements, and then once we have a vertex, then, well, of course, you need to have a kind of a smart data structure in order to be able to delete edges, because if we have adjacency lists, then every edge is on adjacency list of this vertex and this vertex. So you need to have some link between those lists so that you can remove from both, but this can all be done. Right. Questions? Okay, let's go to the second one. Find the number of friends of friends. No, sorry, it's coloring, right. So, anyone has some idea how to do this one? Okay, can you show?
It's like the first question, but in the reverse order. Instead of removing the vertex, we add them one by one in the reverse order that we would remove. So we start with a single vertex, and we add the vertex one by one, but each of these vertex connects to at most 5 of the vertex that we already have in the graph. So we have at most 5 different colors here, and we pick the 6th color to this edge. We do this for each vertex and we color.
That's it. Thanks a lot. And yeah, this can also be expressed in the other order. And this is kind of a magical recursive algorithm that works, but it's a bit counterintuitive. So you can say as follows. To color the graph, we'll use recursion. So assume we can color the graph with 6 colors, and then I'll show you how to color a bigger graph with 6 colors. So it goes like, find the vertex V of degree equals 5. Okay, we can do that. This always exists. And then remove the vertex from G. We delete it. We get a smaller planar graph. So let's say we get a graph. We get a graph G prime. It's G without the vertex we have deleted. And then now we have a smaller graph, so we can color it G prime with 6 colors, right? It's recursion. And after that, we plant V back. So we plant V back into the graph, and we need to color it. But V has only at most 5 edges. So, well, since we can use 6 colors, and at most 5 colors are forbidden, we can always find the right color to color V, right? So this is where the coloring takes place, and this might be surprising, but this is it, right? This is all recursion, nothing more. Okay, does it sound good? Yes, no? Okay. So let's move on to the. Yes.
Sounds strange to me, but in the first vertex, you arbitrarily choose the colors.
Here?
Yeah, the first vertex has at least 5 edges, and you have 6 vertices. In the one with 5 others.
Are you talking about step 1 or step 4? I'm not sure.
The first stage, find the vertex with the
Yeah. So I just find the vertex with low degree. It exists, right?
Okay.
So then I get the vertex. Nothing. I mean, nothing happened so far. I just got a vertex, right?
Okay.
Then I remove this vertex,
Okay.
and I get a smaller graph. I mean, again, it's a planar graph. Now, recursively, I can color it with 6 colors. So this is how recursion works. I mean, we assume that we can do something for a smaller graph, and we should show how to do it for a bigger one, right? So I recursively run the very same algorithm on G prime, and I color it somehow. And then once I do that, I have color assigned to every single vertex of G except for the vertex I have removed, except for V. So when I plant V back, it looks like this. I have V here. It has at most 5 edges. These guys have 5 colors, but I can always find a color which works here. And yeah, it's a really tricky idea. I mean, it's kind of magical because it's not really clear where the coloring takes place for you analyze it. But I think it's good to analyze it for some small graph and see how this algorithm works for tiny graphs to see why is it correct and convince yourself. Right. Any more questions? Okay, let's go to number 3. So the number of friends of friends. Okay, Maybe I'm gonna do this one. So, what is a friend of a friend? So we have a vertex, and the friend of a friend is the vertex V. For vertex V, a friend of a friend is a vertex W, such that there is a path of length 2 connecting them, but there is no edge connecting them. And there is no edge here. So, how do we find those? Let me think for a second. Did anyone mention to solve this one? Yeah, I mean, I'm really sorry, but now I realize I think my solution was wrong too. So, okay, let's. I'm gonna think about this. Maybe I'm not sure. It might be solvable, but maybe not with the solution I had in mind. I'll think about it and either say this is like my idea was totally bad, or maybe we'll give you some idea. Let's not spend too much time here because it's
Nico, is this correct? Well, what I was thinking was that what you need to know is that using that idea that exists just a vertex of degree less than 5 or equal to 5, and you have to keep track of the number of friends. And well, suppose I get my vertex of degree at most 5, right? And then I go to his friends, and his friends will recursively return the number of friends, right? So, well, suppose, well, can I draw?
Yep. Go ahead.
I don't know if it's correct. So, I'll just draw one example here. Well, I have some graph here.
They might be connected, right?
Yeah. And that's my vertex of degree at most 5, right?
Right.
So, well, I will go to his friends, and then I will remove these edges, right? And here, this friend will return to this one the number of his friends, right? So suppose here I have like A1 friends each.
So you mean like the number of edges going?
Yeah.
Okay, we can I think count those in the very beginning, right?
Yeah. Actually, you have to this one have to remove this one, right? So here, this vertex will return to this one A1, A2, A3. So the number of friends of this vertex is actually the sum A1 plus A2 plus A3.
Yeah, this would count those, but this might count this with multiplicity. So if there is a friend of my friend, but we have many common friends, then we might count this guy multiple times. So it's like, so I think what you're counting here is like the number of paths of length 2 here, which is very slightly different from the right. Yeah. So actually my idea was similar to that. I realized there might be a problem here. Okay. Thanks. So that's the last one. The last one is I think the one I like. It's kind of surprising. So we have a planar graph which is weighted this time, and we'd like to find the minimum spanning tree efficiently. Okay, so let me do this one. Maybe. Yes.
What if you just merge the list of the naked neighbors of each of these vertices? Of 5 places?
The, what, what, are you talking about 3 or 4? Three. So what is
I'm trying to fix this.
no?
I mean, you said that there might be repeated vertex. We can merge these lists. There are 5. Yeah, there's 5.
There are 5 lists. Right, but they're could be out, right?
No? I mean, maybe you may sort them and you can go like merge sorting them.
Let me think. Yeah, I think the real problem. I think the problem is actually a bit worse. I think this is not solvable because I thought this would be done in log time, but and actually the output might be big. So if the output is big and we're producing this output one by one, then we might be screwed. So if the graph looks like this. Lots of guys here. So every 2 guys here are friends of friends, right?
But you remove the vertex.
Yeah, what? So I thought that what you were saying is that we'll be counting friends of friends like kind of one by one, right?
No.
No? Faster than that?
Yeah, yeah.
Okay. So because just let me finish this one. So here the answer is big, right? Because every 2 guys here are friends of, I mean, this guy is a friend of this guy, and if we have like n guys here, we get n squared, roughly n squared first, right? So,
Sorry?
so okay, so the output is big. What you're saying is different. So, could you?
Yeah, it's like using his idea, but when we have these 5 vertices, each one have a list of his immediate neighbors, and this list is sorted.
Okay.
We recurse to that. And then we merge them. And then merging, we can remove the duplicates.
Yeah, but merging the list would take time proportional to their length, right?
Yeah, but this time is dominated by the recursion because we recurse on them, so the complexity remains the same.
But I think like if we start in a vertex and then we go to the neighbors, and then we'll basically have some list in the neighbors that we're going to merge and into a list which is like the result for this vertex. And in some sense, the time we spend will depend on the size of the result, right? Because we have to produce a list whose length is as long as the result size. I mean, that's how I understand what you're saying. So I don't know. It feels to me that what you're saying means that that if the answer is k, or I mean the total number of friends in the graph is k, then you'll use more than k time. And because you know, if you're merging multiple lists into a long list, you have to spend time proportional to the length of the result.
Yeah, I mean, but the time to merge the list is like the 5 times the maximum time of each of your recursions. We are paying this time.
But you know, once you recurse, the problem gets different, right? It's first you want to find friends of friends, and then recursively you'd like to. I'm not sure how the recursion works here, because you start with one vertex, right? With low degree, and then I think it's just iteration, right? You go through all these neighbors and just merge all their adjacent to list, right?
Because, okay, I think the point that missing is that when we walk through the merged list, for each of these guys, we add 1 in a counter. I mean, for each guy, you have a counter.
Oh.
That's the result. Then we add 1 in this counter. I mean, we make this guy count us, but he doesn't count us. We add them instead of he adding us. So when we iterate in this guy, he won't iterate in us. We remove ourselves.
So now it feels to me that. So what you're saying is that if we have a guy and an edge, then for this edge we'll spend as much time as the number of neighbors of this guy.
Yes.
So I think this might already be a problem. Like in a graph like this, right? We start this. I mean, every vertex here is pointer. We have all degree 2. So we start here. We go through this edge and then we iterate through all these guys. And then here iterate through all of them.
Alright.
Then we remove, and our problem gets only a bit smaller, but we use lots of time already. I mean, I think this is what we're get this graph. Okay, if you have some more questions, we can discuss it offline, okay?
Alright.
If you have some more questions about this one, let's discuss it offline, okay?
Alright.
Okay. So then let's go to the fourth one, to the minimum spanning tree. Right here. And it's again based on the same idea of a vertex of low degree. So normally you can find a minimum spanning tree with some well-known algorithms in like m log n time or something like that. In planar graphs, we have m is equals to 3m. So yeah, obviously I'm writing m is the number of edges in the graph and is the number of vertices. I mean, I'm using this convention all the time, so I'm not going to define it already. So because of that, this is the same as O and log n. But we'd like to go down to linear. So in order to do that, we find a vertex of degree equals 5, and we'd like to start building an EMST. How do we do that? Well, we simply select the lightest edge incident to this vertex. Why so? So the fact that you may show is that if you have a minimum spanning tree in the graph, then for every vertex, this minimum spanning tree contains the lightest edge incident to this vertex. Right? So, for example, here, my claim is that if the edge weights are like 5, 3, 10, 17, and 8, then the minimum spanning tree would contain this edge. Why is that? Well, if we didn't have this edge, we would be able to add this edge and remove some other. We'll get a lighter tree. Right. So since we have this fact, we get this vertex, we find the lightest edge, and then we contract. So we get this edge and 2 vertices, and then we merge them into one. So this edge collapses, and these 2 vertices become one vertex. Okay, sorry. It's like, and this thing got merged, right? So now we have a smaller planar graph, and we can do the same thing. Obviously, okay, technically we'll have to show that once we contract, then the rest of the minimum spanning tree stays the same, and so on. But I think I'll just give you the general idea without the details here. Yeah, we'll spend already some time on this topic. So, yeah, so, and again here, we can find this vertex in constant time, and once we contract, we can update some messenger data structures in constant time, and then we keep doing that, and in the end, the edges that we have contracted form the minimum spanning tree. This is the idea here. Right, so that was the first property of planar graphs that I believe is very useful, and that's Euler's formula. It's, as you can see, this is mainly useful for speeding things up. So especially here and here, we're just able to speed things up a bit. Well, for coloring, it's a bit different because the structure of the graph helped us. But yeah, the question that you might ask is, when actually does this property become useful? So I think the general answer would be yes.
The fourth question: when you merge two vertices, you remove one edge and one vertex, right? So that formula still holds at less than.
Yeah. So yeah, that's a very good question. Sometimes if you have this situation and you merge those two, then you get something like this, right? You have two edges here, but you only keep the lightest one, right? Because you don't need the other. So because I guess your worry was that this formula would not hold anymore, right? Yeah, but, so you also have to remove some edges on the way. Like if you have parallel edges, then you need to delete all of them except for the lightest one. Then this will help. That's a good one. Right. So so when do we use this property? I think the general answer would be we use this property when the things we're dealing with are local. So this is about answering some local things on the graph. So some edge. So this is not like a path in the graph that goes from one side of the graph to the very other, to the very end. It's something that takes place locally. The same thing is here. It's coloring. So coloring is a local condition. It's about colors of neighboring vertices. And again here, MST is also MST has lots of local properties, and that's why we can use it. So wherever you have a planar graph and you're dealing with some local properties, you should try using this technique. It often helps. Okay, that was it. Let's go on to the second topic, and that's I guess this should be shorter one, and that's separation. The separation property is as follows. If you have a planar graph, let's say this is a planar graph, then there exists a set S of few vertices, such that if we remove those vertices from the graph will decompose into two pieces, and the two pieces will have roughly equal sizes. That's the intuition here. So let's say we have a grid graph, which is a perfectly fine planar graph. A simple grid, which is like K by K. So n is equal to number of vertices in space squared. So in the grid, there is a set of k vertices such that once we remove those vertices, the grid decomposes into two parts which are which have similar sizes. And actually, something very similar holds for general planar graphs. So the theorem goes like there exists a set of S of root n vertices here. K is the root of the number of vertices in the graph, such that removing S causes the graph to decompose into graphs of at most the complement of most 1/3 of all vertices. Or sorry, 2/3. Okay, to be safe. 3/4. This is true for sure. Here it was like a half, but in general it might be a bit different. I'm not going to prove this one. This proof is not very easy. This thing is actually called the planar separator theorem, and it was discovered I think in the 60s. The proof roughly goes like, well, if you have a planar graph, build a BFS tree, so a graph for search. And this would divide the graph vertices into groups, like vertices of distance 1, 2, 3, and so on. And then there are two options. If you get lots of layers, then, well, if you have lots of layers, then it's not possible for every layer to be big. There are too many of them. And it can be shown that there is some layer which is kind of in the middle and it's small. And since these vertices separate the graph. The other option is that this graph is the number of layers is small, and then you can show that, well, you can build a separator which is composed of you have a shortest path 3 here. You can show that there is an edge that together with this tree creates a good separator of small size. Whatever. This is not very important here, just want to give you a very basic idea of the proof. Now, the cool thing about separation is that it opens the way for divide and conquer, right? So think of this graph. We can, if we have some problem to solve here, we can find a separator and then solve it in some sense around the separator, like see what happens around here. And then we can cut the graph and we get two graphs which are much smaller. I mean, their size is supposed to be 3/4 of n. And then we can recurse on the two parts that we get. Okay, so so a simple example here is show this cycle. Is that we're given a planar graph, direct planar graph. The input is directed planar graph. And the task is to find the shortest cycle. The shortest possible in the entire graph. Oh, the graph is also weighted. So how would we do this in a general graph? So in a general graph, we can make a vertex. This vertex has some outgoing edges, some incoming edges. And for a vertex, we'd like to find the shortest cycle that goes through this vertex. Now, if we can do that, we can repeat this vertex by vertex, for every single vertex in the graph, and we'll get the answer. So the question now is how to find the shortest cycle going through a particular vertex. Any ideas for that?
You can take the shortest paths from, if you remove this vertex, you can take the shortest path for each of the vectors that goes through and that goes through. So you can take every combination of the shortest path. You do this slow, but
Okay, yeah, that would work. But, okay. Yes?
You can do a BFS for the vertex, and when you find the first return edge, it's because you found the smallest cycle.
This is me?
Ah, it's okay, never mind.
But actually, it sounded good, you know?
It's found the smallest cycle, but I thought that it was in number of edge, not in.
Yeah, but I mean, I think it's the same, right? I mean, instead of BFS, you'll give Dijkstra. So, but can you repeat your idea?
I thought it was you want to find the number of the minimum number of edges. So you do a BFS from the vertex, and when you find the first return edge, it's because you found the smallest cycle, but in number of edge, not in constant.
Okay, but actually, it also works, right? So what you can do here, in case the graph is weighted, you can compute shortest paths from this guy, like using Dijkstra or whatever. And we get the distance from V to A, B, and C, right? So now, well, the shortest cycle that goes through V, obviously goes somewhere, and at some point reaches one of those three vertices, and then goes back along the edge. So if we take the shortest path from B to B plus this edge, we get the shortest cycle. So the algorithm is like compute shortest path from B, and then once you do that, for every incoming edge of B, check if the distance to this vertex plus the length of this edge, well, forms the shortest cycle. So we do that for this edge, and find the minimum. And this gives us the shortest cycle. Right. So shortest paths. Okay, let's say this is we're doing this for planar graph, so we can compute shortest paths in n or n time. We do this n times because we have to do this for every possible vertex, and we get like n squared log n. Cool. But we can do it faster. Let's use separators. So faster solutions would be, let's focus on a grid graph. This is an easy example, but it's it's actually the same as the general case. So as I said, in the case of a grid graph, no matter if it's square or rectangular, exists a small set of vertices that separate the graph. So here it's the size of the set is root n. Here it's even smaller, right? There is a small set that splits the graph into pieces of roughly equal size. So a faster approach would be one, find the separator. S. Now, let's say this is S. The second step, for every vertex V belonging to S, find the shortest cycle through V. How much time do we need? For the second step. How many vertices are here? Yeah, so we have root n vertices times running a shortest path computation. It's n log n, so this is like n to n root n log n. And then, what happens? Now, there are three options. The shortest cycle is either goes through the separator somehow, touches the separator, is on the right side or on the left side. So once we check all the shortest cycles that have something in common with the separator, we can remove the separator and we get two smaller graphs. And we can do this recursively. Right? We divide and then solve the problem in both halves. So the third step, it would be remove S from the graph and solve the problem in both in those parts of the graph. Recursively. So what would be the running time here? The running time is as follows. So finding the separator can be done in linear time. I'm not going to go into details here. Like for a grid graph, it's quite simple. You just find well, you just check if it's wide or narrow or rectangular, and then find the middle column or the middle row, depending on which one is smaller. And so this is easy. Now this is the hard part, because we have our running time is like, for a graph of size n, our running time is n root n log n plus, well, okay, let's make a simplifying assumption. Okay, for grid graph we can do that. So the subproblems are, the size of each subproblem is at most half the size of the original problem. So we solve it for a separator, and then we solve it for two parts of the graph that we obtain. So we get the following equation for the running time. Do you know what is the solution to that? Well, this one can be this one solves, actually solves this is surprising, but this solves to n root n log n, nothing else. Why so? Well, we can So if we write what it looks like, it's n root n log n plus 2 times n over 2 root n over 2 log n. And then if we plug it in again, it's 4 times n over 4 root n over 4 log n, and so on. So this is the first term. This here, it's 2 cancel out, it's 4 cancel out, and so on. And in the end, we have a sum like n times root n over 2 to the I log n, which is equal to n root n log n times the sum of 1 over root 2 the I power. This thing is constant. This is just a geometric series, and this is constant. Right. So what happened here is using separators. We did something very technical, but yet it enabled us to speed things up. So our goal was to find the shortest cycle, and we showed that it's possible to do it this time. But using the separators, we speeded up the solution considerably. So as I said, we found the separator, and we said that the shortest cycle either touches the separator or it doesn't. If it does, then, well, it goes through some vertex of the separator. We check every possible vertex of the separator and find the shortest cycle through this vertex. And if it doesn't, then we can, well, after checking the separator, we can remove it, and we get 2 smaller graphs in which we have to solve the very same problem. And when we calculate it, we get much better running time. Any questions regarding that? Okay, I think since we've been talking for an hour and 50 minutes, I suggest we make a 5 or 10 minute break and move on to the next topic.
Daí no primeiro falo que talvez eu verificasse com a extra, você tem essa ação. Então você mantém para cada grau do vértice, você vai manter uma lista ligada. Com os vértices que tem aquele grau, uma lista ligada. Aí tipo, quando você pega o vértice, você remove ele, você olha para os vizinhos dele, são no máximo 5, certo? E atualiza o grau dele. Aí tipo, se um cara tem o grau 20, agora ele vai passar a grau 19. Aí você tira ele, remove ele da lista do grau 20 e coloca na lista do 19. Aí você vai fazendo isso. Não, você tem que manter também. Você mantém já o primeiro na posição dele. E aí você vai lá e diminui e coloca. E ele falou então, acho que sempre falou, acho que é essa a multiplicação várias multiplicadas. Não deve.
Não, quando ele vai tirar o resto.
Ah, você quer usar tipo remover a hash?
Aí tem que remover esse E aí tem essa dele que deve resolver.
A marcha não dá para fazer a mesma coisa, você guarda os adjacentes para uma lista, ligado? Aí você vai remover o adjacente e não, então, você pode manter mas tipo, quando ele for inserir uma aresta, você já vai dizer que na aresta A e B, eu vou colocar na lista ligada de B. Então eu já salvo para A, qual o endereço dele na lista ligada de B. Não precisa, porque é uma lista ligada. Qualquer consequência.
Não, é um separate.
Não, isso é a parte mais fácil. O seguinte step é mais difícil que a sua. O seguinte step é mais difícil, são 10 trabalhos.